All right, let me share my whiteboard. Can you see that on your end okay?
Yes, sir. I did have one more question for the midterm. Does it? So sometimes I get stumped or I can't remember how to get started on a problem, and so I look at the help thing where it says view an example. Are there few examples in the midterm?
For some of the questions, yes, sir. For some, there may just be where you can refer back to the textbook, but there are some questions, not all of them, but some have the view an example tool.
Okay.
Okay, lesson 15. We are talking about some more integration techniques. And let me recap the techniques that we've done so far in Cal 1 and Cal 2. Not back substitution, using the power rule in reverse, and also use substitution, and just basic formulas like hyperbolic, cosine, for example. So these are the three techniques that we've been using a lot in this class. And I wanted to go over a couple of more integration techniques with you today. But let's start with this problem. How I know to use substitution with this problem is the highest exponent is at the bottom. And it's actually one more degree than the top exponent. So not in every single case, but in most cases, if you have this scenario, then you can use substitution. So I'm going to let u equal to 2x squared plus 3. And then just take the derivative of both sides. So we have du equal to 4x dx. Now the 4x dx, that's exactly what appears in our problem. So we don't need to divide to get any part of our derivative by itself. We can immediately plug in everything. So the 4x dx is our du, and the denominator is our u. Now, the integral of 1 over u du is natural log, absolute value. Now, before we evaluate our integral, we need to back substitute what u originally was. So u was originally 2x squared plus 3. Now we're ready to plug in our limits of integration. Let me do a check real quick. I think a couple other students have signed in. Can everybody in every location hear me and see what's on the screen?
Yes, sir.
Okay. Now, we plug in 7 first in place of x. So that would be natural log 2 times 7 squared plus 3 minus natural log of 2 times 2 squared plus 3. 7 squared is 49. Times 2 is 98. So that gives us natural log of 101. And when you do the order of operations in the second substitution, you should get natural log of 11. Probably my math lab is looking for you to simplify your answer. So you just undo the quotient rule for natural logs. Anytime you have subtraction, you can write this as one log or one natural log with division. So natural log of 101 over 11 is it. So we are familiar with use substitution. However, I wanted to start off with that type of method and then kind of lean into the others. Any questions, y'all, about the first problem? Some integration may require you to use long division or some type of algebraic manipulation. And that is the case with our next problem. We have the integral of, and this is a fraction, 3x squared all over x squared plus 6 dx. U substitution is out because if you let u equal to x squared plus 6, then your derivative would be 2x. And there's no x at all in our problem. So we have to figure out another way to integrate. Anytime the highest exponent is at the top of your problem, or the highest exponent is the same, like in this case here, we both have x squared, then use long division to first simplify your fraction. So over here, I'm going to take x squared plus 6 and divide it into x squared. Now, x squared can go into itself just one time. And y'all know with long division, you take the 1 and multiply it, or take this part of our answer and multiply it by your original divisor. So 1 times x squared is x squared, and 1 times 6 is 6. Now, if you were dividing regular numbers, at this point you would subtract to get the remainder or the next step. So we just change our signs here to their opposites. And the x squareds cancel, and we're left with -6. So that means we can rewrite our original fraction as 1 and write the remainder over your original divisor. So that would be -6 over x squared plus 6. Any questions about the long division? All right, let's separate our problem into 2 different integrals. We have the integral of 1 dx minus And I'm going to go ahead and move that 6 in front of our second integral. 6 times the integral of 1 over. And I'm going to also swap the terms in the denominator, and you'll see in just a second why I'm doing that. So I'll just rewrite the denominator as 6 plus x squared dx. Oh, there's one thing I left off. So I apologize, and please add this to your notes. I don't know why I just dropped the 3 off the face of the earth. So just add a 3 in front of and put everything in brackets. Now the first integral, 1 dx, that's just x. And this particular form of the second integral is actually a formula. It is 1 over a inverse tangent of x over a, in which x is just x, that hasn't changed. And to find a, because let me put this over here to explain. This is in the form, and you'll see in your formula, this is in the form 1 over a squared plus x squared. That is inverse tangent. Now, you'll probably need a table of integrals. So just search on Google integral tables PDF. And usually the first 1 or 2 hits, you can find a nice cheat sheet. And that way you can print it out and stick it in your notebook. Now we need to find a. Since a squared is 6, then just take the square root of both sides. So a is actually square root of 6. So we didn't need to use substitution here. We just found the right formula and found a. So let's plug a into our inverse trig function formula. We have 1 over square root of 6, inverse tangent of x over square root of 6. And because we're not plugging anything, any limits of integration, you put a plus c to denote any constant. Now, of course, we need to simplify this just a bit. Let's distribute that 3 first of all. So when we distribute the 3, we get 3x minus 18 times 1 over square root of 6 inverse tangent of x over square root of 6 plus c. The last little bit that we need to simplify is that 1 over square root of 6 part. Just rationalize the denominator by multiplying the top and the bottom by square root of 6. So I'll bring the 18 down. And this was simplified to now square root of 6 over 6. The last little bit we can simplify is 6 can go into 18 three times. So here's our final answer, all simplified. 3x minus 3 square root of 6 inverse tangent of x over square root of 6. That part you can leave like it is. You don't have to rationalize it. Plus c. I'll leave this up here for a second in case you're still jotting down the steps. Are there any questions about any of the steps? Now, I don't mind y'all using integral calculator. You can find those on Google also. I actually needed the calculator because at first I had no clue how to even start this problem. So the calculator kind of helped me get started.
See, that's the problem I have sometimes, and that's why I asked about the view an example thing. Is because I look at the problem, I'm like, I'm not sure how to get started on this, and I view an example and I say, oh, okay, and then I can go from there. But
Yeah, if the view and example is not there, I think Ask My Instructor is also available. And you can certainly ask me a question and I can help you without actually giving you the answer.
okay,
Speaking of the midterm exam, let me log in to my math lab. Hold on just a minute. And I can go question by question. It won't take but just a minute and see which questions have you an example with it. I'm sorry, can y'all see Blackboard?
yes, sir.
Okay. So let me go to the midterm exam and actually go to the assignment manager and see if I can change the settings. Uh, I'm just going to go question by question and see which ones have which ones have what help tools. And feel free to jot this down if you want. Or the first question does not have view an example, but it has textbook and also Ask My Instructor. And you will probably not need view an example here anyway because this is a pretty simple question. Question 2 has all three help tools, including view an example. Question 3 has view an example. So does question 4. And question 5. Question 6, yes, view an example. Question 7 just has ask my instructor, but again, it's a simple L'Hopital's rule problem. You may not even need my help, but it's there if you need it. Question 8, again, a simple derivative problem, but if you need my help or need to ask a question, ask my instructors there. Question 9, find the length of the curve. Ask my instructor. And then finally, question 10, this is over lesson 14 on relative rates of growth. You can view an example, refer to the textbook, or ask yours truly if you need help. Okay, let me share my screen again with you guys. Hang on just a second. Get out all this.
Thank you for doing that, Mr. Arnold.
Oh, no problem. I'm glad you asked. Uh, where am I? Oh, there we go. Can everybody see the whiteboard?
Yes.
Yes, sir.
Okay. Let's look at the next problem. Next question, we have a definite integral from 2 to 2 plus square root of 3. And this is a fraction. 5 dx all over 5 plus x squared minus 4x. U substitution would get us nowhere because the derivative of x squared is 2x, and there's not an x in the numerator. So we probably have to do another algebraic manipulation. Now the x squared minus 4x part looks familiar from college algebra. It looks like we can complete that square. So we're just going to rewrite the denominator, not really change it at all. Let's complete the square of x squared minus 4x. Complete the square, you take half of the middle term. So half of negative 4 is negative 2. And then you square it. So negative 2 squared is a positive 4. So now our binomial is squared completely. So we can rename it right now as x squared minus 4x plus 4. Now, before I forget, let me come back over here and do a few things. Let me move this 5 out to the front. And also, because I added a 4 to the denominator, I have to subtract a 4 also to balance it out. Because if I don't do that balancing act, then I've changed the entire problem. So right here with the 5, I'll include a negative 4. Now our x squared minus 4x plus 4 is a perfect square trinomial. So we can factor it as x minus 2 times x minus 2. And that's the same thing as x minus 2 squared. All right, so this part here we know is 1 now. And then this part where we completed the square is now x minus 2 quantity squared. Again, we didn't change the denominator, we just rewrote it into a more familiar format that may fit one of our formulas. Are there any questions about this algebraic part? Now we can use substitution. So I'm going to let u equal 2x minus 2. Take the derivative of both sides. So the derivative of u is du, and the derivative of x minus 2 is dx. Let's plug in everything. Our dx is just du, or 1 du. And our x minus 2 is our u, but it's being squared. Now, the integral of 1 over 1 plus u squared is, again, inverse tangent. I'm sorry, 1 over a times inverse tangent of u over a. So that is our integral formula that we need to use. So up here we have now 5. A is 1. This fits the form a squared plus u squared. So a is just 1. So we have 5 inverse tangent of u over 1, or just u. Now, before we can evaluate this particular integral, we must back substitute u. All right, so u was originally x minus 2. Let's plug in our limits of integration. We have 2 plus square root of 3 and positive 2. And according to our fundamental theorem of calculus, part 2, we'll plug in the 2 plus square root of 3 first. So we have 5 inverse tangent of 2 plus square root of 3 minus 2 minus, remember, a minus sign goes in between your substitutions, inverse tangent of 2 minus 2. Now, the inverse tangent of 0, whether you use a calculator or an online calculator, that's still 0. What we need to find, and you can use the unit circle also to find this value, we're trying to find the inverse tangent of square root of 3. Now, inverse tangent of square root of 3 And make sure your calculator is in radians if you have a fraction button. Make sure you turn that on also. Or you can go online and just type in what is inverse tangent of square root of 3. And that happens at the angle pi over 3. So our final answer, once we multiply by 5, is 5 pi over 3. Any questions about this integral problem? Again, you can use the unit circle, find the angle manually, or you can go on Google, just type in inverse tangent or arctangent, ARC, of square root of 3, and abbreviate square root. You can do SQRT, and Google will read that and find the value for you. All right, let's look at another problem you'll see in this particular lesson. We have, again, a fraction, natural log squared y all over y plus 9 times y natural log cubed of y dy. How I know to possibly use substitution is my exponent, my numerator, is 1 degree less than the denominator. So tell you what, let's let u equal to just the part with the natural log cubed. Oh, before we do that, let's do some factoring. Out of both terms, we can pull out a GCF of y. So when we pull out a y out of both monomials, we're left with 1 plus 9 natural log cubed of y. And what's in parentheses, let that be your u. Now take the derivative of both sides. So we have du, derivative of 1 is 0. And to take the derivative of 9 natural log cubed of y, use the chain rule and power rule. So power rule first, we'll move the 3 in front and multiply it times the 9. And subtract 1 from the original exponent. So that would be a natural log squared of y. Now this is the chain rule part. And if having the exponent in the middle confuses you, what I did was rewrite it. So you can certainly rewrite it as natural log y all cubed. So the chain rule part is take the derivative of natural log of y. The derivative of natural log of y is just simply 1 over y. So let's bring down everything we have. Now, if you compare your derivative to what we were given, we kind of have the 1 over y part and also the natural log squared dy part to plug in. But we have that 27 that we need to get rid of. So just divide both sides of your derivative by 27. And all that really means is when we plug in our u and du, we'll have 1 over 27 in front of our integral. Before I plug in everything, is everybody okay so far? All right, let's plug in everything. We'll move the 1 over 27 in front of our integral sign. The 1 over y natural log squared y dy, that's our entire du up top. And the 1 plus 9 natural log of y cubed, natural log cubed y is our u. So we have a very simple fraction to integrate. The integral of 1 over u du is natural log absolute value of u plus c last step, back substitute u. Final answer is 1 over 27 natural log absolute value of 1 plus 9 natural log cubed y plus c. Any questions about this integral? Next, I want to go over a problem, an integral that has a trig function in it. And this one, again, I had to get help on because I was not entirely sure how to start the problem. So if that happens to you, if view an example is not available, again, search on Google. I don't mind you using any of the online calculators. So this next problem, we have the integral going from 0 to pi over 2 of 24 times the square root, and all of this is under your square root sign, 1 minus cosine theta d theta. U substitution is out because if you take the derivative of negative cosine, that will give you a positive sine theta. And sine theta is nowhere in the problem. Let's see if we can find identity to help us. There is a half angle identity. Sine of pi over 2 equal to plus or minus the square root of 1 minus cosine theta all over 2. Now that formula contains part of our problem, the square root of 1 minus cosine theta. So we need to get that 1 minus the square root of 1 minus cosine theta part by itself, actually. What we can do, first of all, because our integral is going from 0 to pi over 2, we know that sine is positive in that quadrant. So we're only concerned with a positive part. Now, to get square root of 1 minus cosine theta by itself, I'm going to multiply both sides, and be careful, by square root of 2, not just 2. On the right-hand side of our formula or identity, the square root of 2's cancel out. And we have the square root of 1 minus cosine theta by itself equal to square root of 2 times sine of theta over 2. Now, we haven't done a u substitution. We will eventually. What I'm doing now is just a regular substitution. So I'm replacing the square root of 1 minus cosine theta with the square root of 2 sine theta over 2. So we have 24 square root of 2 times sine of theta over 2 d theta. Are there any questions about using this identity? We can use u substitution now. Let u equal to the theta over 2 or 1/2 theta. Because when you take the derivative of both sides, you get du equal to 1/2 times d theta. Well, we need to plug in just the d theta alone. So get rid of that 1/2 by multiplying both sides of your derivative by 2. So 2 du is equal to d theta. That means, of course, we need to pull out a 2 and also pull out the 24 square root of 2. Now, when I multiply that 2 that I got my derivative, we have now 48 square root of 2. The integral of sine u du. The integral of sine u du is negative cosine. So we'll pull out a negative sign out here. Now, before we can evaluate our integral, we must back substitute u. And u was originally theta over 2. Now we are ready to plug in our limits of integration. So starting with pi over 2, we have negative 48 square root of 2, cosine of pi over 2 over 2, minus cosine of 0 over 2. Now, when you simplify the complex fraction pi over 2 over 2, that is actually pi over 4. Cosine of pi over 4 is square root of 2 over 2. And cosine of 0 is 1. Now, let's write what's in parentheses as one whole fraction. That negative 1, we can rewrite it as negative 2 over 2. So that makes our one fraction now square root of 2 minus 2 all over 2. And we got to multiply by negative 48 square root of 2. Let me go back up here. I'm sorry. And where we found the cosine values, I'm going to leave that fraction as is. So square root of 2 over 2 minus 1. And I'm just going to take that negative 48 square root of 2 and distribute it. So we have negative 48 square root of 2 times square root of 2 over 2 minus 48 square root of 2 times negative 1. I'm doing it this way. It's a little easier to simplify. For the first part, 2 can go into negative 48, negative 24 times. And square root of 2 times itself is 2. So that gives us negative 48. And the last part, when we multiply the negative numbers together, that gives you a positive 48 square root of 2. And the very last step, pull out a 48 from both terms. So when you pull out a 48 from both terms, that leaves you with negative 1 plus square root of 2 in parentheses. Any questions about this particular problem? Let me show you how to do another type of integral with a fraction. And this one's a little different from the others. We have 6 minus 72x all over the square root of 1 minus 36x squared dx. What I would do is look through my integral table and see if there's anything that closely matches the denominator. Technically, this is in the form square root of a squared minus x squared. And when you go through your integral table, you'll actually find a formula that fits, kind of. The integral of 1 over the square root of a squared minus x squared is inverse sine of x over a. We'll get to the formula in just a few minutes. Because our numerator has a common denominator, then we can split this integral into two separate integrals. So one of our integrals is 6 all over the square root of 1 minus 36x squared minus the integral of 72x all over the square root of 1 minus 36x squared dx. Let's do the second integral first because our top exponent is smaller than the one less than our denominator's exponent. So I think that indicates using u substitution. So let u equal to 1 minus 36x squared. When we take the derivative of both sides, we get du equal to negative 72x dx. Well, that is exactly what is in our original problem, negative 72x dx. So we can plug in our u and du right away. Be careful when you plug in your negative, this is going to become a positive sign now. Integral of du all over the square root of u. Now the square root of u is the same thing as u to the 1/2 power. But since it's in the denominator, and we need to use the power rule in reverse, let's rewrite u to the 1/2 as u to the negative 1/2 power. When we undo the power rule, instead of subtracting one from the original exponent, you're actually adding one to it. And instead of multiplying, you're dividing by the new exponent. So this becomes u to the 1/2 power all over 1/2. Now, when we divide by the 1/2, we flip the 1/2 and it becomes its reciprocal of 2. So this is 2u to the 1/2 power. And the last step is just back substitute what u originally was. So we now have, and changing this back to a radical as well, 2 times the square root of 1 minus 36 x squared. So that's part of our answer. Uh-oh, I forgot the plus c, excuse me. Now, before we integrate the first part, are there any questions about how we got the second part? The first thing I'm going to do with the first part is move this 6 in front. So that leaves 1 upstairs. Now, our first integral is kind of in the form of our integral formula over here. But we need to get x squared by itself. All we do is either you can look at it one of two ways. You can look at it as you're dividing both parts under the radical by 36. Or another way that you can look at it is that you're factoring out a 36 from down there. So what we're left with is 1 over 36 minus x squared. Now, that's in the proper format where the 1 over 36 is your a squared, and we have x squared by itself. Does everybody see what I'm doing?
Yes, sir.
Okay. Now, a couple of things. This square root of 36 can come out as 6 in our denominator. So really, the original 6 and that 6 we just pulled out cancel each other out. Now, in order to find a to plug it into our integral formula over here, in order to find a, we need to take the square root of 1 over 36. And that's easy, that's just 1 over 6. So let's plug everything into our integral formula and our inverse sine formula. We have inverse sine of just x all over 1 over 6. Now we need to flip that 1 over 6, so that becomes just 6 up top, giving us our final answer, inverse sine of 6x plus 2 times the square root of 1 minus 36x squared plus c. Again, are there any questions about this last problem? Let me show you guys one of the online calculators I used. So give me just a second. Let me switch to the web browser. And I just went to Google and typed in integral calculator, I think. Or you can also go to Bing, Bing.com, and type in integral calculator. And here's an integral calculator that's incorporated into Bing. So let me zoom in just a touch. And you can type in let's do the last one. Let's see, 6 minus 72x divided by, in order for the square root symbol to show up, just type in the abbreviation SQRT and then type in your function. Now, to raise something to a power, just find the little rooftop key is above the number 6 key, and then enter your exponent. So let me double check.
Mr. Arnold, how do you input the limits of integration on that? I know for this problem there isn't one, but how would you?
Oh, good question. Just switch to definite.
Oh, okay. I didn't even notice that there.
I didn't either until you asked me. Yeah, just switch to definite, and you should have spaces here where you can plug in your limits of integration. Oh, yeah. When I typed in definite integral, uh, you just type in your limits of integration, whatever they are. All right, and that is the answer we got. Again, arc sine is the same thing as inverse sine, or arc whatever trig function you're given. All right, this completes lesson 15. I did not go over every single integral you'll encounter, so if y'all run into trouble, just let me know. Use the Ask My Instructor feature in the homework. It's included with every homework problem. Are there any questions about anything from today?
No, sir.